Okay, here we're asked to look at a four-stroke engine, and we're in particular going to look at just one process that occurs in a four-stroke engine. We'll take a look at a moment at a video that kind of shows why this model makes sense. But inside an engine, a four-stroke engine, we're going to see a cylinder. And so let's draw a cylinder, and we'll draw it upside down so that it kind of matches what we're going to see in a second. And inside this cylinder, we're going to assume in this model that there is air in here. Now, air gas. We know in reality that this would be a fuel-oxygen mixture, and that ultimately the cylinder would compress, or the piston would compress this fuel-oxygen mixture, and it would cause, either from a spark or from some kind of auto ignition, it would actually cause combustion to occur. And that combustion is going to happen at such a fast, violent rate that the piston won't have time to move between the time that combustion starts and stops. So it is going to be a constant volume process in which the combustion occurs. So we're going to start off our process here, and we're given a problem in English units. Just to kind of mix it up a little bit, we have a pressure that's given to us of 18 atmospheres, and we have a temperature that's given to us in terms of degrees Rankine, 1241 degrees Rankine. And we now have a constant volume process, so this will be, I believe, the second time we've seen this. So V is a constant here. And that means that we really know that at state 2, the volume is going to be the same as the volume at 1, which is just a single volume. And we probably should circle these two guys, because even though this is in English units, nothing has changed in terms of the science. We still know buy 2 get 1 free from the equation of state works, and we can get the volume from this. So at state 2, what we are told is that the temperature after the combustion has occurred is increased quite a bit. It's now at 3600 degrees Rankine. And so our question is, what is the pressure at that second state? So just as before, we can see that very likely what's going to determine our problem is the equation of state. Our governing equation is an equation of state. It's going to tell us about how these two relate to the third that we don't have. An equation of state is determined by the substance. In this case, even though we know that this is a combustible mixture of oxygen and fuel, we're going to model it as air. So this is going to be kind of like the air standard approximation. And we're going to model this air in the gaseous phase, obviously. So let's once again choose the ideal gas law, where now R is going to have units in English in the imperial system, rather than the SI system that we've been using up till now. And instead of going through our normal route, where we kind of plug in numbers individually, let's look at each state and then try and plug the states together. So we've got that the volume that we're ultimately interested in, that's going to be equal to RT on P. And that volume at state 1 indeed is the same volume as it is at state 2. So I could write something that looks like this. Let me change this. Got ahead of myself. Maybe I'll explain this. So at state 1, I've got this operating, but at state 2, the volume is just given by RT on P at 2. So obviously this ratio is constant, and so I can cancel out certain things. And since I'm interested ultimately in P2, let's solve for that. So P2 in this case would be equal to P1 times T2 over T1. And the nice thing about this is that now I really don't have to worry about too many unit conversions, because these temperatures in degrees Rankine are going to, their units will cancel out. So I'm going to get something that is going to have the units of whatever P1 is, in this case 18 atmospheres. So now that we've kind of taken a look at this, let's go ahead and do it in MATLAB. Take a quick look at a four-stroke engine. This is just Wikipedia, and I recommend that you read the article. But what you're seeing here is a piston, and so at the intake phase, air is brought in, and then it is compressed, and you can see a spark ignites this mixture, and we have burning, and then in the last phase it's pumped out, the exhaust phase. What's interesting, and what hopefully you're seeing by this, is at the instant that the spark happens, combustion occurs instantly, and the piston hasn't had time to move. So boom, it's right there. That's the whole process. The constant volume process happens practically instantaneously right there. So that's what we're talking about modeling, this very small volume when it's all compressed and the spark ignites and combustion occurs inside the piston. And we're modeling this very simply. Instead of really looking at the fuel-oxygen mixture, we're just going to use air. So let's take a look at how we would do this in MATLAB very briefly. So this is almost too simplistic to have to worry about MATLAB, but let's do it anyway. So start up a file and start with the secret sauce, and basically we're looking for P2. All right, so what's this going to look like? P1 times T2 over T1, and this is going to be in the units of P1, which we already know as ATMs. What is P1? It's 18 ATM. T1 is our 1241 Rankine. T2 is 3600 Rankine. And so this problem is also, if we wanted to plot it, which we don't need to, it would be a straight line like our last linear or our last isochoric problem. And so here now we've got a pressure of 52.2 atmospheres. Even though this is a really simple problem, and in fact if you wanted to solve it more robustly, inside Sengel's book he has tables not just in SI units but in English units, so you can very easily find the appropriate value for R, even though it uses the evil pound mass unit for mass in the English system. Nonetheless, you can find these, and they will indeed work out if you continue to use all the same units that you ought to and just keep track of them. But we really didn't need to do that in this case, and we can see that really MATLAB is just a calculator. And by doing it in MATLAB, we can kind of keep track of what we have done in the past. So doing something in MATLAB even this simple, I don't think that you've really lost any time in comparison to just doing it on your calculator. So that is this very simple piston problem.